All right, let's talk about the hyperbola. It's one of those shapes you've definitely seen in math class, but the real why behind it, what actually makes it tick, that can be a little fuzzy. Well, today we're going to fix that. We're going to peel back the formulas and get to the one simple, beautiful idea at its heart. Let's get into it.
Okay, first things first. Before we even touch an equation or a graph, what is this thing? What's the core idea?
So just look at this shape. You've got these two perfect mirrored curves kind of sweeping away from each other. It looks pretty complicated, doesn't it? But here's the crazy part. Every single point on both of those curves is obeying one super simple rule. So what could it be? What's the secret instruction here? And here it is. This is the secret sauce. A hyperbola is just a big collection of points. If you pick any point you want on either of those curves and measure its distance to those two special fixed points, we call them the foci. Okay, got those two distances? Now find the difference between them. The magic is no matter which point you pick, that difference will always be the exact same number. That's it. That one simple rule is what creates this whole amazing shape. And this constant difference isn't some random abstract number. It's something you can actually see and measure right on the hyperbola itself. It's the exact distance between the two closest points on the curves, the tips, which we call the vertices. We label that distance 2a. So the rule that creates the shape is literally baked right into its own dimensions. Kind of cool.
All right, so we've got the main idea locked in. Now let's get the terminology down. Let's learn the names for all the different parts so we can talk about this thing properly.
Okay, here's the whole shebang. This is our master diagram. Think of it like our roadmap for this section. Now, I know it looks like a lot at first glance, but don't worry. It's just showing how everything we're about to talk about fits together. We're going to go through it step by step. So let's start with the skeleton of this thing, its axes. The big one, the main one, is called the transverse axis. See how it slices right through the middle, connecting the foci and the vertices? And its length? Well, that's our old friend 2a. Then, running perpendicular to that, you've got the conjugate axis, and its length is 2b. These two axes are like the scaffolding that the whole hyperbola is built on.
Okay, let's quickly run through the other key players here. You've got the foci, those are the two magic points that started this whole thing. Then the vertices, which are basically the turning points of the curves. Right in the middle of it all, you have the center. And then, see those dotted lines? Those are the asymptotes. They're like invisible guardrails. The curves get closer and closer and closer to them as they shoot off to infinity, but they will never, ever actually touch. Pretty wild. So you might be wondering, is there a way to describe how wide or open a hyperbola is with just a single number? Yep, there is. It's called eccentricity, and we use the letter E for it. And for every single hyperbola that has ever existed or will ever exist, there's one golden rule. E is always bigger than 1. Always. So we've seen what it looks like, we know the parts, we get the core idea. Now for the really cool part. How do we boil all of this beautiful geometry down into a single, elegant piece of math? Think about it. Everything we've just talked about, the foci, the vertices, that constant difference rule, even those asymptote lines, it can all be captured perfectly in one little equation. It's pretty amazing. And here it is. X squared over a squared minus y squared over b squared equals 1. Now, the superstar of this equation is that minus sign. That's the key. It's the minus sign that creates the two separate branches. The A tells you where the vertices land, and A and B together, well, they define the whole shape we just talked about. Okay, that's great for a hyperbola that opens sideways, along the x-axis. But what if we want one that opens up and down? What do we have to tweak? Well, have a look. On the left, that's our familiar friend, opening left and right. But on the right, we've got what we call a conjugate hyperbola. It's basically the same idea, just flipped 90 degrees. You can see the foci and the vertices are now on the y-axis. Same shape, different orientation. So how does the equation change? This table lays it out nice and clear. For the conjugate one, the y squared term is the one that's positive. It comes first. Just by swapping which term is positive, you flip the whole thing. And naturally, that means the coordinates for the vertices and foci shift from the x-axis to the y-axis. It's so simple, but so powerful. All right, to wrap things up, let's check out a really cool special case, a kind of perfect hyperbola. So let's ask a what-if question. We've got our two main axes, right? The transverse and the conjugate. Their lengths are related to A and B. So what happens if they're equal? What if A equals B?
Well, when that happens, you get the rectangular hyperbola. It's sometimes called an equilateral hyperbola, and it's easy to see why. Just look at the asymptotes. They form a perfect square in the middle. It gives the whole thing this really clean, perfect symmetry. It's just elegant.
And here's the cherry on top. For this one specific, perfectly symmetrical hyperbola, the eccentricity isn't just some number bigger than 1. It's always exactly the square root of 2. How cool is that? A perfect number for a perfect shape.
So I'll leave you with this final little puzzle to chew on. We've spent this whole time talking about how a hyperbola comes from a rule of constant difference. So what if you flipped the rule? What if you took those same 2 points, but instead you looked for all the points where the sum of the distances is constant? What shape do you think that would make? Something to think about. Thanks for joining me.